Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And here we go into limits at infinity for Calculus 1. This is kind of the next set of let's say epsilon delta proofs, even though they're not epsilon delta proofs. And we're going to approach this in a similar fashion as we did with epsilon delta proofs. These are much easier though than the finite limit at finite point cases. Instead of developing the proof and really focusing on proofs here, we're going to focus a little bit on just evaluating these limits and seeing how to do that, because that's actually going to be the lion's share of your work with this material. So let's see here. Let's start again with evaluating finite limits at infinity. The definition, and this is the non-rigorous or the layperson's definition of a finite limit at infinity. We're going to let f be a function defined on some interval, some positive interval by the way, a to infinity. A technically could be negative. It's not that big of a deal. But we have a function whose domain is at least some finite number a to infinity. Then the limit as x approaches infinity of f of x equals L means that the values of our function can be made arbitrarily close, can't say that word, arbitrarily close to that limit L by allowing x to be sufficiently large. Now let me just showcase a visual of that, because reading that out loud does you no good unless you see a visual. So let's suppose we have some function. Our function is in blue here. And as the function runs off, or maybe I should say as the x values run off to infinity, notice that our function values get closer and closer to that green line, y equals 5. This is a very easy function to create on your own, what I've written here. This is like a sine function in a way, with being multiplied by e to the negative x, for example. And you could check that out on Desmos if you want, try it out. But you could see that the blue function there, f of x, is definitely approaching a height of 5 as x goes to infinity. And so if you look at the actual non-rigorous, but still slightly on point definition, we can allow our function to get arbitrarily close to our limit L. And by arbitrarily close, really what I'm saying is, if somebody gives me an epsilon neighborhood, let me draw one in here. So I've created this epsilon neighborhood. Somebody just walked in the room and said, oh, you think that function gets really close to 5? I bet you can't make it close to 5. And you say, I can. And they say, prove it. What if I give you an epsilon neighborhood of size 0.1? And so what they're basically saying is they're wiggling around the height of 5 by 1. So this height right here would be 5.1. And this height right here would be, or the y value, would be 4.9. And they're saying that they're challenging you to force your function between those two epsilon bars. Well, if you look to the left from the very beginning, our function definitely is outside of those red epsilon bars for a while. But as we scroll to the right, eventually our function does get captured in, my drawing is terrible. Our function does get captured to within those epsilon bars right about, let's say here. From this point forward, notice our function will be within those epsilon bars. And so that's some large number. I'll just call that large number m. For some large number m and forward, for all x values greater than that, I could see that my function will be within those epsilon bars. For a better visual, I suppose I could use Desmos. So I'm just slapping together something very quickly. I just threw together a function. It's like a sine function lifted up 5 units, but the coefficient of sine is a decaying exponential function. So that just decays the amplitude of the sine function. And I'm claiming that this function will eventually tend to a height of 5. And somebody walks in the room and they give you an epsilon neighborhood of 0.1. So actually, I'm going to make it somewhat smaller here just for our purposes. So I'm going to say they give you an epsilon neighborhood of 0.01. So 5.01 to y equals 4.99. So they've given me a very small epsilon neighborhood. So small, in fact, that you can barely see the epsilon neighborhood on this graph. Okay. And they're claiming that, you cannot prove to them, and let me color these a little bit. There we go. And they're claiming that you can't get this function within this epsilon neighborhood. And you say, yes, I can. I swear that I can. And they say, prove it. And you say, okay, I will. Let me just scroll to the right here. And you can see that, well, it's going to take quite a while. So I'm going to quickly go through this. I'll zoom in, or maybe I'll just keep dragging over. Maybe I'll drag over quickly like this. You can see it does decrease in amplitude as I do this, but it's still not within those epsilon bars. Eventually, though, it will get there. It just takes quite a while to do it. It would be much easier if I just zoom out and scroll to the right a few more times. Now, I've zoomed in quite a bit here, but I just want to show it. You can see that our function, those are the epsilon bars, they go from 4.99 all the way to 5.01. And you can see that our epsilon neighborhood, our function is still slightly below this. Let me zoom out a little bit so I can drag faster. But you can definitely see it's below. But now watch what happens. It's going to cross in, and let's see what happens as it climbs up. And again, I'm going to zoom out just to get it faster, going a lot faster here. And if you zoom up, you'll see that this time when it climbs up to the top here, it looks as though it does. It still crosses over, but now, zooming out a little bit more, it's going to come back down, and let's see what happens here. I know this is exciting. This is wonderful. It doesn't look like it actually goes below in this region. In fact, it doesn't. It looks like it barely is a little bit of airspace. So this is perfect. This, I think, is perfect. From this point forward, yeah, the graph is going to stick within this epsilon neighborhood. And if I zoom out and drag to the right, you will hopefully see, yep, there it is, it's climbing up. And it'll just bounce in between because it's now within the epsilon neighborhood forever and ever. So we have found an x value or a time point, a time where this function will now wiggle within this epsilon neighborhood. And I can just say, for example, let me try to click on this and keep it. From x equals 93.679 onward, I know our function is within this epsilon neighborhood. That's really what the general non-rigorous definition of an infinite limit or a finite limit at infinity is. Now, I spend a lot of time on a concept like that, mainly because it is basically the proof. That's how the proof runs as well, is that you want to find that x value such that from that point forward, your function is captured within that epsilon window. And that just makes the knowledge of the proof a little bit easier for us. There is a secondary piece to this because not all x values run to infinity. They might run to negative infinity. And so the other half of this is just saying, what if instead our function was defined on negative infinity to a, and we allowed x to wander off to negative infinity? Well, if the limit as x approaches negative infinity of our function becomes finite, like a 7 or something like that, that means that the function itself can be made arbitrarily close to that limit value, again, let's say 7, by allowing x to be sufficiently negative. Like how negative? Like less than whatever point where from that point forward, your function's wiggling within some epsilon neighborhood, but in a negative direction. I hope that makes sense. I really I don't spend enough time in these videos talking about how much I want my students to succeed, because these videos that I'm making right now are just for the general calculus public, I suppose. But specifically to my students, I want you to know, this is a plea to my students. I want you to succeed, and I want you to truly understand this stuff because it's really cool stuff. And once you get it, it really does lock in. You kind of really do get it. Now, before we go jumping off into examples, I'm just going to state a couple theorems that are going to help us. We will prove them later on, but for now, I just want to state them. If you have a value of r, which is a rational number, not an irrational, but a rational number, such that x to the rth power is defined for all x values, then the limit as x goes to infinity of 1 over x to the r is equal to 0. Now, I hope for most people that makes sense, because if you think about just 1 over x, which is not supposed to be written in highlighter, but if you think about 1 over x to a power, okay, and as long as that power is positive, well, that function in general, it's not always going to be this way, but I'm just going to pretend as though it's an integer power. So like a natural number, like a 3 or 4 or 5, it's going to do this. That's if, by the way, it's a natural numbered power. But as x goes to infinity, you can easily see the function gets closer and closer to a height of 0. That argument still holds if the power is not a natural number, but instead a rational number, like a 1/2 or something like that. It still holds. It's just a little bit harder to draw. But still, anyway, I hope you get the point. You should hopefully naturally just say, oh, x is going to infinity. Sure, 1 over x to a positive power should tend to 0. That should be like natural at this point. If that's not natural for you, let me remind you that a finite number over super huge will always tend to 0. There you go. That's the reminder. And kind of a corollary to this is if your base is, it's not really a corollary because it's kind of completely different. That last theorem, the x was in the base, right? So it was x to the r. That was, let me actually use highlighter. I'm going the opposite direction here. So in this case, we had the limit as x goes to infinity of 1 over x to the r, which, by the way, is the same as the limit as x goes to infinity of x to the negative r. Same thing. Okay. Now we're switching it up. Instead of having the variable in the base, what if we have the variable in the exponent? Well, here I'm specifically picking on the natural base raised to the variable exponent power. And that's because you're STEM students and you're going to be dealing with natural bases almost exclusively. So let's think about this. And I'd like to focus actually on the second one first. As x is allowed to roam off to infinity, you have e to this power that has a negative on it. But this power is super huge. In fact, instead of writing p, I'm just going to say super huge. And this will tend to 1 over e, because you can rip the negative off the exponent, little algebra, law of exponents. That's going to be 1 over e to the huge. That's 1, or a finite number, over a massively huge number, which will tend to 0. That's not a proof, that's a justification. We will do a proof way later on, but still, or maybe I assign that to my students as a homework. It's actually very easy proof, but you'll see something like it in today's lecture, or in this video, I should say. Likewise, if instead of having the negative explicitly written in the exponent, but instead we have the negative just hidden within the exponent, it's the same exact thing. You allow x to go to negative infinity, well, you have e to the negative huge power. That's 1 over e to the huge, which again tends to 0. And as is written below, we will do this later as a proof. Those two pieces of information are critically important for you to understand, because you can't move forward in calculus without really understanding the reasons why those statements are true and without proving those statements. So let's go ahead and start into some examples here. And I'm trying to pick on examples that you would normally see in a college calculus course, and some examples that might trip people up. let's have a little warning here, because this one, I've been teaching calculus for such a long time, I can easily tell you there are a lot of issues with this style of problem, even though technically it's not so bad. Some junk approaching infinity minus some other junk approaching infinity is not necessarily zero. You're in calculus, folks, and in calculus, you're playing with infinities, and infinities are wicked things. They don't act the way they don't obey the normal laws of arithmetic. So you can't just say like, oh, well, 3 minus 3 is 0, so therefore a picture minus a picture is always 0. That's not true. A picture, or basically in this case, a concept called infinity minus another concept called infinity is not always 0. You have to be very, very careful. Also, I'm going to highlight this word, approaching. Those values are not infinity, they're approaching infinity. One might be approaching infinity faster than the other. Now, I say that warning, and watch, this example will probably turn into 0. That's still okay, because I'm saying it's not necessarily 0, but I'm not like saying it's never going to be 0. I'm saying sometimes it's not going to be 0. That's okay. So let's go ahead and go back to this example. How would you do this? Well, one of the things I tell my students is in a calculus course, when you see a difference of terms, one of which is a radical, and you cannot do direct substitution, you better believe you got to multiply by conjugates. So in this case, you cannot do direct substitution, because this would be something approaching, it's not equal, it's approaching infinity minus something else approaching infinity. And that, we do not know what that is. It's indeterminate. We have no idea what that's going to turn into. And so we need to manipulate this. And this just reminds me, like, this is the most dangerous section for students who don't pay attention, because when they don't pay attention, they do that. Oh, it's infinity minus infinity, so therefore it's 0. And I see that all the time. Because I give you the warnings, I am heartless on grading. So if you end up just saying, oh, infinity minus infinity is 0, I'm going to say, great, so is your grade. So you don't want that, right? You want to be armed with the best information so that you can dominate your calculus course. You want your teacher to go, man, this student is awesome, and I want all my students to be awesome or sufficiently decent. All right, so let's go ahead and jump into this. I think I've harped enough on this. I'm going to go ahead and just multiply numerator and denominator by the conjugate. Notice each step of the way, I'm modeling good behavior by writing the limit. You should write the limit each step of the way. If you don't, you're wrong. You should do all of this within a limit. I usually have this problem when students have seen calculus before, and they had an instructor who allowed them to not write limits, that they just do all their arithmetic without limits, or their algebra without limits. You need to do that with limits, period, because it's not correct if you don't. All right, so there we go. I've multiplied numerator and denominator by the conjugate. Of course, the denominator on this guy is just 1. Distributing out the numerator, right? Again, my word of advice to my calculus students is when you multiply numerators and denominators by conjugates, really only distribute out the conjugates themselves. Don't worry about distributing out the non-conjugates. That is, multiply these two highlighted things together. If this down here was not 1, but instead, let's say it was a 5x plus 4 or some silliness like that, you would not distribute out against the square root of 9x squared plus x and then plus 3x. You would not do that. So you would only distribute out conjugates. It just, trust me, is the right thing to do. And when you multiply conjugates, you should know they are actually differences of squares. So that numerator is going to be just a 9x squared plus x minus a 9x squared. You can double check my algebra there if you want to. Divided by the square root of 9x squared plus x plus 3x. And now algebra before calculus. So I'm going to just continually clean this up. So the 9x squared's up in the numerator, canceled beautifully. And I end up, again, writing my limit sign here, or my limit notation. It's not a sign. I end up with this, x over the square root of 9x squared plus x plus 3x. And you look at that and you say, hey, that's still not that great to deal with. And I would say, well, it isn't. I would agree with you, because if you look at the numerator is tending toward infinity. And if you look at the denominator, the entire denominator is tending toward infinity plus infinity, which that is actually infinity. Okay. Infinity plus infinity, you're safe to say that's infinite, but infinity minus infinity is the indeterminate form. All right, so we have infinity over infinity. And before somebody emails me or states in the comments down below, hey, can't you just use L'Hopital's rule? I will just tell you right now, no, you can't, because at this point in a calculus course, you've not been taught that. So that's an illegal move. Do not do that. You have to showcase proficiency with limits before you're allowed the luxury of shortcuts. So that being officially said, don't do it. In your calculus class, in my calculus class, just don't do it until you're allowed to use L'Hopital's rule. If you have never heard of L'Hopital's rule, good. You're probably better off. All right. So what do you do in this situation? Because infinity over infinity, junk approaching infinity divided by some other junk approaching infinity is not necessarily 1. So notice the two warnings I've written down. In arithmetic, they would be true, like a number minus itself, that would be 0 in arithmetic. And a number divided by itself, that would be 1 in arithmetic. But you're not in arithmetic, you're in calculus. And infinity, that's a concept. So all bets are off. You cannot say, oh, I have something approaching infinity divided by something else approaching infinity, therefore it's 1. Nope. That, now that you've been warned, that is, you just can't do that. That'd be bad news. So please don't make that mistake. This is not necessarily 1. It might be, but it's not necessarily 1. So what do? Well, you treat this rigorously. And here is the idea. You want to divide both numerator and denominator by the largest power of x in all the terms. Let me write that down. I tried to fit it on the screen there. Divide numerator and denominator by x to the pth power, where p is the largest power of x in all the present terms. Now let me just give you a piece of warning here. When I say the largest power of x, if you look at the numerator, that has a power of 1. Well, that's pretty easy. Looking at the denominator, that 3x on the back end, that's a power of 1. Looking at this first entire term, the largest power of x is not 2, because you're taking its square root. The square root of x squared is x to the first. It's not actually x to the first, but we're going to say it is. So the power on that is not 2. That's a power of 1 as well. Let me write that in blue. So p is equal to 1 there as well. Because again, you're having the power, taking half of the power of each object or term within that radical. So the largest present power of x in all terms within that fraction is just x to the first. So I'm going to divide everything by x to the first, and I'm going to write it this way. This is equal to, and off to the left-hand side, I'm just going to say divide both numerator and denominator by x to the first. So I'm just kind of stating that here. So our limit as x approaches infinity becomes 1 over, I'll write plus 3 on the back end, because obviously that's what that last term is when you divide it by x to the first. And let me go ahead and just zoom in here. This is the square root of whatever it was, 9x squared plus x, and you're dividing that by x. Now let's go ahead and mention something incredibly important here. So the thing I want to showcase here, and it's might be done differently by different instructors. Everybody's slightly different with this move, but I'm going to do it my way, mainly because it reinforces an idea that you learn in algebra. So I'm going to write this as the limit as x goes to infinity of 1 over. And I am going to take that square root and I'm going to factor out that x squared off of both those terms. So I'm left with 9 plus 1 over x. That's what happens when you divide off an x squared off of both those terms. Now, normally, when you do this, you won't be this slow. You'll actually go much faster than what I'm doing right now. But I need to showcase something here so that you really truly understand what's going on. So again, I don't expect you to take this amount of time on a problem like this. It actually goes a lot faster than what I'm doing, but I want you to see the method behind the madness. So this is, let's see, I'm just breaking up that radical. So far, I hope you're okay with that. I just broke apart that square root of a times b into the square root of a times the square root of b, where a is x squared and b is that 9 plus 1 over x. Now here's where an important note needs to be made. You may not remember it, but I'm just going to repeat it because it's incredibly important. The square root of x squared is equal to the absolute value of x. A lot of people think it's equal to x, but that's not actually true. And you could see why. Maybe I should state that here. If you took a look at, let's say, the square root of 3 squared, I think most people would be okay with saying that's the square root of 9, which is 3, and everybody's happy. But if I traded that out and said it was a negative 3 being squared, well, again, that's a square root of 9. Square root of 9 is 3. Notice what happened when your argument was negative. It forced it to be a positive 3. The square root will always return a positive number. And so you have to be very careful when you're dealing with even roots. So it's not just squares, by the way. It is, if n is even, then the nth root of x to the nth is the absolute value of x. Again, that's true if n is even. If it's odd, you don't have to worry about the absolute value. Okay. So over here, we have the square root of x squared. That's going to be the absolute value of x. And this is where I'm going to really focus in on where x is heading. So let's see, this is the absolute value of x times the square root of 9 plus 1 over x, all over x, and then plus 3. Again, very long-winded, but there's something very important at the end of this. Notice x is positive here. X is going to positive infinity. So there's really no reason to have the absolute value. So this is where I'm going to say, it's perfectly okay for you to erase those absolute values because x was going to infinity. Sorry about that little line up there. So this is going to be 1 over x root 9 plus 1 over x divided by x plus 3, and the x's in that denominator cancel beautifully. And in the end, you get the following. The limit as x goes to infinity of 1 over the square root of 9 plus 1 over x, and then plus 3. Now, we have a theorem we just learned. If you have 1 over x, let me highlight it, and the power on x is a rational number, and x is going to infinity, that piece right there, we have a theorem, that piece right there is going to 0. Now, there are several rigorous ways of writing this. I know some instructors who will force you to do the following. They'll say you have to write this as 1 over the square root of 9 plus the limit as x goes to infinity of 1 over x. I didn't need that square root that large, I guess. And then plus 3. In other words, they brought the limit into the numerator and denominator, and then the limit of 3 is just 3, so they don't worry about that. And the limit of a radical is the radical of a limit, and they do all the limit laws to get to this point. And then this, we have a theorem that tells us, that approaches 0. That is the most rigorous way of dealing with that. However, I'm somewhat forgiving with that as an instructor, and I am perfectly fine with students going to this point and saying, oh, but I have a theorem that says 1 over x as x goes to infinity approaches 0. Thus, this is equal to, different color pen, this is equal to 1 over, notice I'm not writing limit anymore. Once I take advantage of evaluating the limit, there's no need for me to write the limit anymore. So this is just going to be 1 over the square root of 9 plus 0 plus 3. Or in other words, 1/6, right? Root 9 is 3, so 3 plus 3 is 6. Now, I freely admit that's a lengthy problem, and it need not be lengthy. If it was a homework or an exam and somebody was working on this, here's what you would likely do. I spent a lot of time talking about all this stuff, but the reality is you would start at the top and you would say, oh, I have a difference of 2 terms, one of which is a radical, and I see this is approaching infinity minus this is approaching infinity, so I can't just plug infinities in. So instead, I'll multiply by the conjugate. So everybody would do, I'll put green little arrows here. Everybody would do that step. Everybody would do this step because you have to do the algebra to simplify it. And everybody would get to here. That you can't avoid. And then everybody would divide by x. So everybody would go ahead and divide by x. But when they do that, most people would skip all of this conversation and just get to this, because they're so used to dividing by x. So once you get used to dividing by numerators and denominators by x, and as long as you are firmly aware of this piece right here, then you're okay. So a lot of people just get there and then just evaluate. It's a very fast evaluation once you get used to it. So this limit, which was infinity minus infinity, ends up being 1/6, not 0. Ha ha. In your face, people who think infinity minus infinity is 0. Ready to do it all over again? Well, you're not going to have to, because this is going to negative infinity. So this is a different question. So let's see. I have x approaching negative infinity. Well, we've got some issues. Several of them, in fact. First thing is, I know that this is going to should return a positive number, so it might return infinity. And I'll guarantee it will, and I'll tell you why in a moment. This one will return negative infinity because x is tending to negative infinity. And again, we're at infinity minus infinity. Now, I want to convince you, as an aside, why this is approaching infinity. Because you might just say, well, it's because 9x squared, and you're allowing x to approach negative infinity. When you square it, it becomes positive infinity. That's true, but you're also losing infinity off that. So let me showcase to you why 9x squared plus x approaches infinity. And some people will think, I know why, because 9x squared is infinity bigger than negative infinity. And it is kind of true, but that's not a good argument. So, just as an aside, I'll write it here, aside. I should have used blue for some reason, that just bothers me. 9x squared plus x is the same thing as x times 9x plus 1. I sure hope you agree with that. That's just algebra. And if you allow x, so as x goes to negative infinity, x times 9x plus 1 approaches negative infinity times negative infinity, right? This is approaching negative infinity, and 9 times negative infinity, well, still negative infinite. If you add 1 to that, it doesn't suddenly become positive. It's still negative infinite. And so there you go. Negative times negative. That's the only arithmetic that actually works with infinities. Negative times negative is still positive. So that's wonderful. And that's why I'm telling you that picture is approaching infinity. And when you take its square root, it's still infinity. Anyhow, so this is going to be infinity minus infinity. That's what it's approaching. And so we know that's a no-no. We don't know what that's going to be. So we're going to multiply both numerator and denominator by the conjugate. Ready, set, go. This is equal to the limit. Remember, you always write that limit notation. If you don't, you're wrong. This is going to be the square root of 9x squared plus x plus 3x. And then you're multiplying it by its conjugate, both numerator and denominator. Now, while I'm writing, I am going to clarify. I can write and talk at the same time. That's not what I'm clarifying now. I am clarifying something that I'm kind of a stickler on. I tell you that you have to write limit every single time. But you know what? To be honest with you, if you're just using algebra, if you're doing algebra on the side, like massaging the problem a little bit, let me just simplify that and do some algebra. Technically speaking, you can do the algebra on the side and then reinsert it into your limit. So you could do all of this notation here without writing limit, and you can clean this up without writing limit, but eventually you're going to have to go back to the problem and say, okay, so our original limit is now equal to the limit as x is approaching negative infinity of 9x squared plus x minus, 9x squared all over square root of 9x squared plus x minus 3x. So eventually you'll have to get to that anyway. Or actually, really what you get down to is this, because the 9x squareds cancel. So this is what you would, if you had done the algebra on the side, that is technically okay. It's just eventually you do have to write the limit notation. And myself and several other mathematicians that I know who teach are sticklers about making sure you just continually write limits, because often students who do the algebra on the side will forget to write limits when they do their calculus. And then I can't give credit because this is a calculus class, not an algebra class. So let's take a look at what we have right now. Notice, by the way, this is something that I always do. Every step of the way, once I've cleaned things up, I then recheck. What are things doing? Well, that's approaching negative infinity because x is approaching negative infinity. This is approaching positive infinity because, well, that's what we said it was approaching earlier. And this minus 3x, so this picture right here, is approaching minus 3 times the negative infinity, or a positive infinity. And so now you see, actually, arithmetically, we're doing okay. Infinity plus infinity, I know that's infinity. The problem is, I have infinity over infinity, and I don't know what that's going to turn into. Probably not 1. So, what do I do now? Well, divide both numerator and denominator by x to the first. So I'm just going to write that off to the side. In blue here, I'll just say divide by x, divide by x. That's totally okay. It's legit to do that move. See how I use the kids' lingo these days? It's lit. All right, so let's go ahead and do this. I don't know if I just said something dirty. I have no idea. Limit as x is approaching negative infinity of 1 over. I'm going to write this as 1 over x for now. And I remember that I can factor out of this radical here. I can factor out an x squared. And the square root of x squared is the absolute value of x times the square root of 9 plus 1 over x. And remember, minus 3. We divided that by x on the back end. All right, so what happens now? Well, here's where you have to be very careful. The absolute value of something, well, if that something, which is a happy face in this case, because math is happy, if that object or the argument of the absolute value was non-negative, there's no need to have the absolute values. You could just erase them. And that's where you would get this picture right here. However, if the argument inside the absolute value was negative, well then you need to take its opposite to force it to be positive. That's what an absolute value is going to do. So it'll take its opposite if the interior or the argument of the absolute value is negative. It's going to take its opposite to force it to be positive. Well, if you go over to our problem here that we're working on, we have this absolute value of x right there, just sitting there waiting to be worked on. But x itself, I know is negative. So the argument of this absolute value is a negative number. I'm allowed to remove the absolute value signs, but if I do so, I have to replace it with a negative x, the opposite of x. And so again, this is why I harp on that definition so much, is because it's incredibly powerful in calculus. So we get to this point right here, and you see this is different than the previous problem. We did it much faster, but still different. And so this will be the limit as x approaches negative infinity of 1 over a negative root 9 plus 1 over x, and then minus 3. Remember, as x goes to actually plus or minus infinity, 1 over x approaches 0. And so once I make that note for my instructor, hey, I know 1 over x is approaching 0, everything else is fine, now I can continue forward without the limit. I can say this is equal to then 1 over a negative root 9 minus 3. That's a negative 3 minus 3, or negative 1 over 6. Ta-da! A lot faster, right? But it's because the reason why it's faster is I didn't have to go through all of the theory that we talked about earlier. Now that we've gone through that, there's no need for me to spend forever talking about it. By the way, you also should note, I speak very quickly. It's not my fault. I have a genetic condition that forces me to speak quickly. That is not true. It's just the fact it sounds like an excuse, and it sounds like a good excuse, so I'm going to say it. Before we dive into this example, let's talk about a warning. I've been saying it over and over again that limit laws can only be applied if the sub-limits exist in our finite. That is, you can break or split limits as long as those breaks become finite. I say it all the time, but no matter how many times I say it, about a third or a quarter of the students still break this law. And I'm just letting you know, if a problem is worth 100 points on an exam and you break one of the limit laws, I don't give you credit. So it's very important that you pay attention to what I'm telling you, even if I speak quickly, right? So if you say, oh, he's asking me to evaluate this limit and I'm working on an exam, so let me see if I can apply a limit law, and you try to do this, oh, this is the same thing as the limit as x approaches infinity of e to the negative 2x times the limit as x approaches infinity of cosine of x. Oh, look at that. This is approaching 0, and 0 times a number is always 0, so this limit must be 0. I would say, yeah, that's your grade 2 on that, because you've just broken a limit law. Remember, you can make that split fine. That's okay. You could try it out. But this number that you've said it is, that is not a number. That limit does not exist. The cosine as x goes to infinity wiggles, 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 wiggles. So that limit does not exist. So you do not want to split this limit and say, oh, 0 times anything is 0. This number, when you're working within a limit, this is not 0. It's approaching 0. So that's incredibly important to state. This is calculus. These are not like concrete numbers. They're things that are approaching concrete numbers, but while they're within a limit, they are not like concrete 0 or something like that. So this is a bad move. Don't do it. Boo. So then you say, well, what do I do, Professor Simpson? Because I just don't think I can do anything with this. Let me erase that. And I would say, there is something you can do with this. Because of the fact that this limit has a piece that does not exist, you might be able to use some other theory we've learned. Remember that when I covered a topic a while back, and I said, sometimes you're dealing with limits and there's a bad guy within that limit, some type of function that's just misbehaving. Well, This guy is the bad guy in this limit. It just doesn't exist. I'm going to point at him, and I'm going to call him the bad guy. All right. And so if that's the case, we might be able to bound the bad guy. Well, I think I'm really good with that. I'm going to trademark that. Bound the bad guy. Bound the bad guy. So let's bound that bad guy and see what happens. So I know that the cosine of x, well, that's always bouncing between and including -1 and 1. Now I'm just going to rebuild the argument of the limit there by multiplying all three sides of this triple-sided inequality by e to the -2x. So I get negative e to the -2x is less than or equal to e to the -2x times cosine of x is less than or equal to 1 times e to the -2x. Notice I have our function bounded above and below. What do you think we're going to use? You should already be saying it out loud or in your head, or maybe to your neighbor, or call up a friend and just say, I know what he's going to use. And they're going to say, what are they talking about? You are going to use the squeeze theorem. You know that the limit as x goes to infinity, because that's what x is tending to, of negative e to the -2x is 0. Why do I know that? Because this is that theorem that I said we would prove later. Limit as x goes to infinity of e to the -x, okay, fine, we have -2x, whatever, is going to be 0. So we're using that. Likewise, I happen to know that the limit as x goes to infinity of e to the -2x is also equal to 0. So not only, so this is kind of a nice way of writing that the right-hand limit, left-hand limit, both equal 0. It also showcases that they're squeezing something. So by the squeeze theorem, the limit as x goes to infinity of e to the -2x times the cosine of x must also be 0. And that's something that is, I mentioned it when we learned the squeeze theorem, that it's super powerful. It gets used a lot. And here you see it's used even with infinite limits. Again, I want to reiterate, every time you use the squeeze theorem, you should say, by the squeeze theorem. All right. And I also want to reiterate that I started this problem by saying you cannot break that limit into two sublimits. Because again, people will say, but that approaches 0, and this is just some other number, and 0 times numbers are zeros. And it turns out, yes, I get it, the limit ended up being 0 in this case. But I'm letting you know it's not always going to be like that. So it's safer, much safer, and actually proper to use the squeeze theorem on this. You cannot split that limit. Be very, very careful. Don't split limits that do not exist, where the sub-limits don't exist and are not finite. Now, for my students who have the printed lecture notes and they're looking at the next example and they're about to say like, hey, he didn't cover this in lecture. I'm going to skip this problem for the time being because I want to introduce the actual, true, precise definition of the infinite limit when we go into the next series of videos, because that's the way that you would work with this problem. Naturally, I think most people are going to say, well, this limit does not exist because the first piece tends to 0 and the second piece just does not exist. It keeps wiggling forever. But if you do that, if you make that argument, you're essentially saying I'm splitting the limit, and you can't split that limit. So it is illegal to split the limit to evaluate this. So I will wait until I give you the precise definition of the finite limit at infinity before we come back to this problem and showcase why this limit does not exist. Okay, so if that was all mumbly junk to you, that's okay. We'll see it in the next video. All right, you guys, have a wonderful day. And I hope your calculus course is going splendidly. I hope that you have colleagues in the course to lean on and to commiserate with and to complain with and to say your professor's awesome with. All right. Talk to you guys later. Bye.
What's the system of equations? We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.